We now talk about the product of sums form. This is not very common, but you realize it's also very valuable when you are solving or simplifying the expressions in Boolean algebra. And we say that Boolean expressions can be written as an add operation of OR functions. And when we do that, we call it, or we refer to it as product of sums. And again, this is very simple. We need to say that assume you have a variable y, that you have variables expressed as product of sum. So this is a sum. You multiply with another sum, maybe with another sum. So this is an OR operation, same as that one, but they are joined together with add operation, and therefore this is product. Product is the one that comes first of sums. So we are simply saying that we are having an expression that is expressed as product of sums. Sums is given by OR operation, product is given by the add operation. So we have another example here that says assume y is expressed as such. This again is a product of sum, because this is a sum, another sum, and another sum, but they are joined together with an add operation. We say that each of the logic terms in the above expression is called a max term. So this one term here that is achieved using an OR operation is considered to be a max term. So this other a max term. This one is also a max term. Therefore, you have product of max term. So a Boolean expression in three logic variables will have a minimum of 8 max terms, just like we did with the sum of products. And we can be able to express such a product of sums as this one. For us to express this as max term, which we are going to be expressing it with capital M, we are going to be saying that this is a 0, 0, 0. These are not min terms. Remember, we used min terms. We were using ones to represent min terms. So we use zeros to represent max terms. For that reason, if we are to represent A or B or C, we are going to say that whenever A is not complemented, that represents a 0. B uncomplemented, that is a 0. So this is going to be a 0. Whenever we have, so this is 0, 0, 1. Whenever you find a complemented or a bad variable, that is the one that represents a 1. So this will be a max term 1. 0, 1, 0. So that becomes max term 2. 0, 1, 1. Max term 3. Similarly, 1, 0, 0. Max term 4. All the way up to where we have 1, 1, 1. We have max term 7. So we can now formally define the max terms by saying that the max terms are defined as follows, that M0 is represented by all the uncomplemented variables A, B, and C. M1 is just as I said. So for us to easily remember is that when you're talking about max terms, no, not min terms, and they are in this form, notice that the uncomplemented variable is represented by a 0, and the complemented variable like this one is represented by a 1. And for that reason, you can now be able to say that this 001 represents a max term 1. Similarly, 010 is equivalent to max term 2, and 011 is equivalent to max term 3. So finally, the others are represented as follows. This is max term 4, max term 5, max term 6, and max term 7, just like I showed you when I was alluding to this earlier. So again, the max terms are designated to correspond to the respective cells in the K-map, and the logic expression y can be written as a function of max terms, and therefore we can say that y is not now sum of products, but rather product of sums. This is sum, this is sum, and all of them are multiplied, and therefore they are expressed as product of sums. And we normally use pi, capital M, to represent this as a product of sums, and we normally identify the sums that are in that expression inside the bracket. So a K-map can also be used to simplify such an expression in POS form, and that is when we identify what we have said earlier, that zeros are used to represent a variable that is a max term. So for example, we are told use a K-map to simplify the following Boolean expression. How do we do that? We say that the expression f can be written as a function of max terms as follows. So there are two methods like we have done earlier, whereby you can expand such a function, because we identify here we are missing a c. So assume if you introduce a c, how would it fit out? They will take two possible values, uncomplemented form of c and a complemented form of c, and therefore when we introduce it, we say that then it can be expressed as 1100. 1100 is equivalent to max term 12, and this becomes 1110. This becomes max term 14. So that is why we are saying that this can be expressed as such. Another method we can do is just to create our K-map and feed in, and then we notice which columns and which rows will represent our max term, but we'll see that shortly. So we will see another example here that says that we have A, B, C, D, and we can see we are missing variable B here. Therefore, we put it in and identify which values it might take, complemented form and uncomplemented form. And when we now interpret these ones, they become max term 12 and max term 8. Simply again, we say this is as whenever we find a complemented form, we say this becomes 1100 1000. So this is why we are seeing 1100 becomes max term 12 and 100 becomes max term 8. Notice that here we are always using capital M. So finally we have max this term. So what we are trying to do is to represent this one here, this one here. Now we have said this is now equivalent to 15, and now this one is simply 1101. This is equivalent to 13, and finally this is not a positive, this is not a negative, so this one is 1010, and this should represent a 10, and that's why we are saying this comes there. And therefore the final expression for f should be pi, meaning it's a product of max terms. Then we arrange them in the numeric form, which is 8, 10, 12, 13, 14, 15. 8, 10, 12, 13, 14, 15. And this may be expressed as M8 dot M10 dot M12 all the way up to M15. And as you can see, that is what we are representing here. All we have not done is to rearrange. The final expression is, as I have mentioned, f is a product of sums 8, 10, 12 all the way to 15. And now we look at the product of sums example. We see that the expression f is entered in the K-map by inserting 0 for each max term that I have mentioned before, and thus zeros are inserted in the 12, 8, 13, 15, 14, and 10 as I have already illustrated. So we look for the groups of zeros that are formed, and then we identify what those groups represent. So again, we have said that we have f is equals to product of max terms 8, 10, 15. And if you remember, we have A or B here and C or D here. Notice the change in notation. This is 0001, just like we said earlier. Let's first of all name the cells 0, 1, 2, 3, 8, 9, 12, 13, 14, and 15. So we put the cells 8, we put as 0, 9 as 0, 10 as 0, and 11 as 0. We don't have a 0 in 11. 8, 10, 12. So these are the zeros we have that represent our example. And we now group the groups of 4, which is this one, and then this other group of 4, which is this one. So we then identify what does this group represent, and this group represents 1 is a bar, as we said. This is a bar or B bar. Just notice that unique representation when we have where we have changed from how we represented sum of products to the product of sums. Whenever we find a 1 in POS, because it is represented by a 0 is going to be a bar. So we say this is A or B bar, this is A or A bar or B, this is A or B bar, and this is without a bar. And similarly on this side, we say this is equivalent to C or D without any bar. This is C or D bar. This is C bar or D bar, because zeros are the one that are used to represent the max terms, and for that reason, whenever we have a 1, that's a bar, and D. So we have C bar D. Therefore, when we are now just speaking, we just speak what we have here. This is A or B bar. And this group of 4s, we can see that in this case we have D is not changing, or A is not changing. So this becomes A bar or D bar. Therefore, we say that we can represent F as simplified form as A or B bar and A or D, which is equivalent to this form. So most of the times this is the final form that you need, but if you are told to express it using the product of sums, you give it as such.